Picking up on part C, talking about particle diagrams for things when they're dissolved in water. So we're going to draw all of these in the solvent of water. As a reminder, we drew water on the first page of our notes, but water has a shape like this with 2 lone pairs on your oxygen. And so we describe water as what type of molecule? Bent, and because of its bent shape, it's what? Polar. Good. So polar means that it has a positive end and a negative end. So somewhere on this molecule is going to be positive or positively charged, slightly positively charged, and another end is going to be slightly negatively charged. We say slightly positive versus negative because the electrons aren't truly being taken away from one atom or the other. They are being shared in this bond right here, but because of the oxygen's electronegativity, it's going to hog the electrons in this shared bond. So yes, they're technically shared, but they're going to hang out more towards oxygen. And these electrons in this shared bond are going to hang out more towards oxygen just because oxygen is more electronegative. Plus the lone pairs on oxygen mean that this part, I'll circle in a different color. This part of the molecule is more negative. It has a slight or partial negative charge. Versus the other side, the hydrogen end would have a slight positive charge. So this is just a refresher of what we drew before. So kind of as like a shorthand way to draw this now, make it not too thick, like that. As a shorthand way of drawing this, we're going to draw water with a circle and a circle and a bigger circle. Where this one, like the single side, is going to be your oxygen, and then these two are your hydrogens or your partial positive side. Or you might see it drawn in a different orientation like this, meaning your partial positive is up here and your partial negative is down there. So this orientation is going to matter when it comes to slight negative, oops, almost made that positive, slight negative, slight positive, partial negative. Okay, so that orientation matters when it comes to how we show our ions dissolved in water. So if I go to my first one and I have SO3, we need to first determine if SO3 would be polar or nonpolar, because remember that if you are in water, water will dissolve polar substances, and it also dissolves ionic substances. So either things that also have a slight negative and slight positive charge from a covalent compound, or things that are actually positive or actually negative. So if I have SO3, I zoomed in so that I could draw it. My sulfur would be my central atom. My oxygens would be symmetrically arranged around my sulfur. I would use a single bond to tie each of the oxygens to the sulfur. Sulfur has 6 valence electrons, and oxygen also has 6 valence electrons, and I have 3 of them, so 6 times 3 would be 18, which means that I have 24 electrons to work with. I just used 2, 4, 6, which means I can subtract 6, so now I have 18 that I need to put around my oxygens. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I used all 18 of my electrons, assuming that there are no exceptions to our octet rule in this case. Because remember, sulfur can have exceptions, but if we assume that there's not an exception since nothing is listed, is everyone stable?
Yes.
What does stable mean? Full valence shell, okay. And so I just said no exceptions to the octet rule, meaning everyone needs how many to be stable?
8.
Does everyone have 8? Okay, so then are we stable? No. Okay, so then to make it stable, if we're not stable currently, to make it stable in this case, after I've used all of my electrons. So my oxygen here is stable, this oxygen is stable, and that one's stable because they all have 8. But my sulfur, my central atom, is not stable. I can't just make up an electron to give to it or make up a pair of electrons. Yes. What? Yes, you can put a double bond, but how am I going to do that?
You take away one of the pairs from the oxygen.
Perfect. Okay, so here's a case where we would have a resonance structure. So you can take away a pair of electrons from any of the other oxygens. Oops. So if I put that oxygen back, I took away a lone pair so that I can shift it into be a shared pair or a double bond. I just picked that oxygen because it looked good to me, but you could pick any of the oxygens, and that's what makes this a resonance structure. So these electrons would actually be delocalized, and it would shift between the different bonds. Do you remember what shape we would call this? Try something. I like the try start. Trigonal planar, perfect. Okay, so the difference between trigonal planar and trigonal pyramidal, remember, is that trigonal pyramidal had a lone pair on the central atom, but here we don't have lone pairs on our central atom. It's just 3 different atoms bonded to my central atom, so that would make it trigonal planar.
Trigonal. Yep, that's the right.
Would it be polar or non-polar?
It's trigonal, not trigonal.
I mean, people pronounce it differently. I say trigonal, but trigonal, I guess.
Non-polar?
This one would be non-polar, so the charge is evenly distributed, especially because those electrons are delocalized. So if this is a non-polar substance, the SO3, would it dissolve in water? No. So we can show it by having SO3. I'll just show it as a molecule thing. So we'll have this, this, this. I'll call that my SO3. And then to put water in here, if I make this a little bigger. In terms of the positive and negative end of your water, it doesn't really matter. Water would just kind of be in there, and it's not going to dissolve anything. They wouldn't mix. My pen stopped.
You know something, Ms. Wilson?
Yeah.
I thought whenever I was younger that I would, whenever I was in high school, I would be learning, the movies where there was, the models of things and, and I got so scared, and then I came here and I'm like, this is none of that.
We could pull models out. It's just yeah. Everything's digital, I show you the digital models of the molecules. I have little water magnets where I have the oxygen and the hydrogen, and they act like water molecules, but I just didn't feel like playing with those this year. But we can do it if you really want. That would just take the place of one of our actual fun labs that apparently aren't that fun.
They are! That's so bad.
Okay, so next one is MgCl2. If I were to draw MgCl2, what would right away be different that you should notice? Perfect. It's an ionic compound, so the electrons are truly going to be transferred, leaving you with just an ion. So in this case, there's really not any reason to draw it. What you're going to be left with is magnesium, with a +2 charge, and you would have chlorine with a -1 charge. And I guess you would technically have 2 chlorines. So when you draw that, what I want to see is that you took your water molecule and you orient it the correct way. So I'm going to continue drawing them like this. You don't have to show me the positive and negative as long as you have the 2 hydrogens on one side and the oxygen on the other side. I want you to show me how that water would be oriented around whatever your ionic compound is. So for the magnesium that has a positive charge, would the oxygen end or would the hydrogen end of the water be closer to it? Yeah. Closer to oxygen, right? So then the single side with the hydrogens facing away from it. I'm going to make that fatter. little bit, please. Whoa. Good enough. Okay. So my single oxygen with the hydrogens facing away. Single oxygen, hydrogens facing away. Single oxygen, hydrogens facing away. Versus our chlorines, since they are negatively charged, my water is going to face a different way. So my hydrogen ends would be closer to my chlorine, leaving the oxygen on the outside. So this one ends up almost like looking like a star because the positive hydrogens are attracted to the negative chlorine. Make sense? All right, let's do the next one. CuClO4 Is this ionic or covalent?
It's ionic.
Ionic. So that means I would be left with little copper plus 2 ions and perchlorate minus 1 ions. ClO4 minus 1. And again, because of the 2, that would tell me I have 2 of them. So if you really wanted to be accurate, you could draw both. ClO4 minus 1. And then I'm going back to drawing my water. So it would be the same kind of orientation as it was in the previous example, where if I have a negatively charged ion, my water would have the hydrogen end facing that ion. So you can draw your little like V shape first, and then go back in and put your dots on there. And this one would be the same way. Boom, boom, boom. So again, the like open end is representing the hydrogen side. So I'm going to keep going back to this picture so that you don't forget what we're actually drawing. This is like a reduction of this. So this is the true picture of water over here, but we can abbreviate it for the purpose of showing the orientation in here. So this would show me that those negative ions are dissolved in water and the positive hydrogen end is oriented towards that. And then this one would be the opposite, where the negative oxygen end of my water would be towards my positive copper ion. By the way, I could tell that it was a positive 2 charge because the 2 would have come from copper. Yes.
Does it matter how many V's or like molecules?
No, just like several. Ideally, you would surround it completely. So like that's what I'm trying to show, is that the process of dissolving something, if you remember from our first page when we gave actual definitions, the process of solvation is surrounding your solute particles with solvent particles. So if you were going to demonstrate on this like particle diagram that something is dissolved, then I want you to show me that you actually surrounded solute particles with solvent particles. And so here, if I say, okay, here is my solute and my solvent is water, then I just want to see that it's surrounded. So there's not like a specific number, but it should be like a pretty close to closed circle around it. Yeah.
So then if you're drawing something that's not dissolving, they wouldn't have to surround.
Right. So that's why I drew this one, like they're just separate and it's not surrounding it because it won't dissolve since it's a non-polar solute. And then if I have C5H12, C5H12 is going to be a carbon chain. So those end up kind of looking like this. This isn't exactly what it would be. But we can go ahead and just call this nonpolar. The way that you can tell is if you have carbon and hydrogen. I know we didn't really practice drawing these. But one of the rules that we did learn is that hydrogen will never be a central atom. So you know that if you have multiple carbons, you'd have carbon bonded to carbon, carbon, carbon. 1, 2, 3, 4, 5. And then 12 hydrogens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There would be a hydrogen on each of those. So it would be a long carbon chain. And so in organic chemistry, a lot of times this is abbreviated as like a zigzag line like I had at first. But if you're looking at this, there's nothing on here that would indicate that this molecule would have even the ability to be polar in any way. You know there's not going to be a lone pair like just randomly throughout one of these things. So yeah, nonpolar. So if it's nonpolar, then that means you've got your molecule. In this case, I'm just going to write C5H12. That's fine. And then for my water, I can still show that it's put into water. Like, you can put anything into water, but that doesn't mean it's going to dissolve. And so I've just got like random water molecules that are going to stay separate. And they're not oriented any kind of way. They're just there. Like that. Okay. So nonpolar, there's no positive end, there's no negative end that's worried about. All right, we're going to go kind of quickly through the next one. So this is talking about redox reactions, or just refreshing your memory on different types of reactions, and then we'll focus on kind of more specifics in a second. So redox reaction, do you remember how we would identify those?
A reaction using a single element.
Perfect. It contains a single element on either the reactants or the product side. So the 4 examples of redox reactions that we have already learned are synthesis, decomposition, what else? Combustion, and single replacement. Perfect. Is double replacement a redox reaction? Perfect. So when I taught this, I taught redox as basically the opposite of double replacement, because in a redox reaction, you have a single element on one of the sides of your reaction, versus in a double replacement reaction, you have 2 compounds trading partners and creating 2 new compounds. So our acid, base, and precipitate reactions, these are the double replacements. That was the other thing we learned. In an acid-base reaction, this is a type of double replacement reaction that contains a compound that begins with hydrogen on the reactant side of the equation. If something begins with hydrogen, what type of compound is that? Acid. Good. So this is why it's called acid-base. Acid. We'll see the base part in a minute. And it has water on the product side somewhere. So it would be actually water plus a salt if we want to be more specific. Water plus salt. Remember that a salt is any ionic compound. And then we'll do an example on the next page, so don't worry about that yet. And then the other type of double replacement reaction is a precipitate reaction. This is one that contains ionic compounds on both sides of the equation. One of the products is going to be your precipitate. That would make it an insoluble salt. So insoluble is the same thing as precipitate, or it would indicate that something would form a precipitate. And then the other product is a soluble salt. The soluble salt forms your what? Do you remember? Not the precipitate, but if you remember using this chart before, when you looked something up, it was either going to be soluble or insoluble. If it was insoluble, perfect. We called it precipitate if it was insoluble, and if it was soluble, we called it the aqueous solution. And then again, I'm going to just do examples on the next page. Same thing as up here. A salt, remember, is any ionic compound. So this one's saying salt and salt. We're just talking about any compound that's a combination of a cation and an anion. All right, this next little section is just a refresher, again, on determining the precipitate versus aqueous solution. If something is insoluble, it means it will not dissolve. Oops. In the solvent. So if it will not dissolve, that makes it the precipitate. And if something is soluble, that means it will dissolve in the solvent. So that is your aqueous solution. If it's a precipitate, we would write an S by it to indicate that it's a solid. So as far as the states of matter, that's the little things that go in your parentheses. And if it's soluble, it'll be aqueous. So it says use the solubility chart to determine if the following compounds would form a precipitate or be part of the aqueous solution. If I have KCl, I would look up my anion, the second part of it. So my chlorine is in the section that says soluble, and then I just need to make sure that it's not bonded to one of my exceptions. If this is too small for you to read, I also printed the solubility chart bigger on the back of your notes. It's the exact same thing. So if you flip your notes packet to the very last page, you have that there as well. So for potassium chloride, is this going to be soluble or insoluble? Soluble. And does that make it a precipitate or an aqueous solution? Perfect. Then NH4OH. OH is down here in the section that says insoluble, but also NH4 is listed, so you could really look this one up either way. NH4 is the only cation that's listed. I'm not really sure why that is. Probably just because it's a common exception for a lot of things, is that it's always going to be soluble. So either way, if you looked it up with this one, you would get that it is soluble, or if you look it up here, it says insoluble, but NH4 is specifically listed as the exception. So this one would be soluble, and that makes it aqueous. And then BaSO4. My SO4 is up here in the section that says it's normally soluble. However, if it's bonded to barium, that is a common exception, meaning it's going to do the opposite of what section that it's in. So barium is actually going to make SO4 insoluble. So we would call this what? Perfect.